Thank you for joining us for this opening session and awards presentation. As we've explained many times to people wondering why we use Oakland as the name for our conferences held in San Francisco, San Jose, Berkeley, Paris, or now in Zoom land, Oakland is not a place, it's a community. This conference has a long and glorious history going back to the first symposium held in 1980. As part of our 40th anniversary celebrations last year, Stefan Savage initiated the Test of Time Awards to recognize some of the most significant results this community has produced. Last year, papers from the first 15 symposia were recognized, as well as papers from 2007 through 2009. I had the immense privilege of chairing the committee to select the Test of Time Awards from the 1995 through 2006 symposia, which will be presented today. After that, Avi Rubin will present awards for the 2008 through 2010 symposia. Selecting award winners from all the remarkable papers published across 12 Oakland conferences is truly a daunting task. It would not have been possible without the tremendous efforts of an amazing group of committee members who you see here. Our committee spans the entire history of the symposium with expertise across the breadth of research in security and privacy and a deep understanding of both the academic research community and industrial practice. It was a true pleasure and an extraordinary honor to work with this group. Our charge was to identify papers that had stood the test of time. We considered three main criteria. First, the paper should describe work that has had a substantial impact on the real world. There are lots of ways such impact might be realized, but the most obvious ones are having a direct influence on common practice across the computing industry or being deployed in widely used and important systems. The second main criteria is having a major impact on the research community. We did look at bibliometrics as one factor, but didn't emphasize citation counts as a way to measure this. Instead, we looked for papers that initiated major new research directions and led to work or even entire research fields that otherwise would not have emerged. Finally, we wanted to find papers that anyone in our field should read and learn about today. We started with the 252 papers published in the 12 symposia. All of these are good papers. As we all know, Oakland never accepts a bad paper. One of our goals was to find papers with outstanding impacts, but that might not already be well known among our community. So I assigned to each member of the committee a few years of the time period to look at, with a task to scour all the papers from those symposia looking for candidates that satisfy the test of time criteria. We identified 31 candidate papers for a short list to evaluate more thoroughly. Over a series of Zoom meetings last winter, we discussed all of these papers in length and selected 9 papers to win Test of Time awards. It is my distinct honor to present these awards, which will be announced in chronological order. We invited each of the award winners to prepare a short video to share the story of their paper, and I think you'll find many valuable lessons and insights to glean from their experiences. The first award is for A Sense of Self for Unix Processes from the 1996 Symposium.
What a lovely honor to receive this award. Anil, Steve, Tom, and I would like to thank all the organizers through the years who have worked so hard to sustain the symposium, which today remains as one of the most respected venues in security. Of course, we are particularly grateful to this year's awards committee, who dredged up our paper for the award. A heartfelt thank you from all of us. The occasion has brought the four of us back together to reminisce a bit. Our mindset was quite different because we were coming in from different disciplines.
We're more like scientists and engineers. A lot of the security papers I'd read up to that point were more like, they sort of didn't, they weren't as empirical as that. They didn't, maybe there were a lot of theoretical papers, but they just didn't go to the trouble of trying to run attacks. I mean, obviously for good reason, it was really hard to do that. Yeah, it was all such a big unknown as to whether this approach would give us any joy. It wasn't any theory we could turn to or anything like that, really. It was just hunches, right?
That stuff that, we wanted to do and get it involved, I don't think it's going to work. As I said, they just, there's just not enough there to discover the anomalies and separate the traffic. I'm like, you just can't do it.
Bill and S-Trace did not get along well.
No.
The other thing that I think was unusual about what we did is using such a simple modeling method.
It's a cry of where's the reproducibility is still a cry. It is still a bane of the existence of so many of the security papers out there.
We still lack on our computers even something that's circumventable, but just something that is a general defense against a wide classes of attacks. We tackled a hard problem, and that problem still hasn't been solved. And we want to encourage everyone to look back and say, there are still room for crazy ideas to solve the big problems.
I want first to thank the community and the committee for this Test of Time award of a paper that we worked on 25 years ago, and it was part of Adam's master's thesis. Adam and I started to think at that time about the implication of the fact that the internet gives attacker global reach, and what can they do. And the twist was that they can weaponize cryptography and use it as an attack weapon rather as the traditional defense that it always used to be for confidentiality and authentication and things like this, protective measures. So we came up with this work. We envisioned that the internet will be there, global reach, that attackers will persist on the internet, and that they will try to extort money and make illegitimate business over the internet. That electronic payment system will come, and this is how this paper came to be, Cryptovirology. And we continued to think about offensive cryptography and continued to pursue this new role that we envisioned that cryptography can play as an abuse and attack tool. So thank you very much.
Hi. On behalf of my co-authors, Joan Feigenbaum and Jack Lacy, I wanted to say that we are honored, humbled, and to be honest, a little bit baffled that you've chosen to honor us with the Test of Time Award for our paper. When we wrote this paper, we, I think, misunderstood what its impact, to the extent it's had impact, would be. We thought that we were proposing a compelling alternative to the identity-based X509 style certificate model that was starting to emerge on the internet and be proposed for general use. And I think it's probably fair to say that we completely and utterly failed to succeed at that goal. But we also, I think, accomplished something a little different that may ultimately be why you chose to recognize the paper. And that is that we identified an explicit trust management layer in secure systems where a dangerous request coming over the network should be scrutinized at a specific layer of abstraction. And I think we've seen that impact over time percolate out into many of the services that we see. And we're just delighted that you've chosen to recognize that we and the work that preceded us in this area had some influence over that. And again, we're humbled and delighted and honored to receive this terrific award. Thank you very much.
Hello, I'm Gene Spafford. When we received notice of this award, we were all a bit taken aback. 23 years? Has it really been that long? Let me give you some context for how the paper came about. In 1992, we founded the Coase Laboratory at Purdue University. As one of the only academic research areas in cybersecurity in the world, we attracted many talented students, including the co-authors on this paper. In 1996, there were a number of internet denial of service attacks. I challenged the students to look at the attacks and try to come up with a solution. They quickly replicated the attack and started in. After a week or two of effort, we had a group discussion that included the students presenting a detailed discussion of how the attack worked, including using the TCP diagram as an illustration. The solutions they had come up with so far were disappointing in scale and efficacy. I remember suggesting that if they could model the attack as a state machine, then perhaps a solution could be developed the same way. Within a week, the students had coded a working prototype to test our model attack and defense. Thereafter, with some extended tinkering and tuning, there was a rush to produce a paper to submit to the conference, a process I'm sure many of you have experienced. Thereafter, Christoph received his PhD in 1997 and is now a senior security architect at Apple Computer. Yvonne received his PhD in 1998, and he currently runs a company, Art Exacta, that he founded in Bolivia. Markus finished his master's in 1997 and went on to finish his PhD and join the faculty at Cambridge. Robin finished his master's in 2017 and is now the head of information assurance and data protection at Relix. Diego finished his PhD in 2001 and is now an enterprise security architect at Swisscom in Switzerland. In 1998, I transitioned Coast into the Sirius Center at Purdue, which I led for 18 years. Currently, I'm continuing as a professor at Purdue and generally as a curmudgeon at large. We would all like to thank you for the recognition of this paper. It remains a bright spot in all our careers, as does this event today.
I'm David Goldschlag. When Paul Syverson, Michael Reed, and I began onion routing in 1995, we never imagined that it would be important in 2020. I'll give some history before Paul talks about the paper. People ask why the US government let us build onion routing. The company line is that we were not trying to provide anonymous communication, but to separate identification from routing. And to protect government open source intelligence collection, you needed other users. But the truth is, we knew that privacy was important and that anonymity was controversial, and we were happy to be mischievous. We never imagined that onion routing would be well known or be a question on Jeopardy or in Business Week. When my son Kobe began high school, the get-to-know-him question was, whose dad invented the dark web? But we didn't invent the dark web. I'd like to thank the IEEE and NRL, Carl Landwehr, Kathy Meadows, and John McLean, and most of all, both Michael and my carpooling buddy, Paul.
I'm Paul Syverson. We started on onion routing at NRL 25 years ago. Michael and David moved on after the 90s, but I'm still at NRL and I'm still working on onion routing. The largest legacy of this work, and this particular paper, is undoubtedly the system that Roger Dingledine dubbed Tor, or the onion routing, to distinguish it from versions devised elsewhere following our invention. Paper's contributions include the first description and performance analysis of an onion routing implementation, one that was publicly available and in use since '96, and the first mention of a configuration where clients build circuits locally but are not themselves on onion routers, so we're no longer limited to a peer-to-peer model, and lots more. Currently, Tor's millions of daily users rely on a nonprofit employing dozens of employees, and a huge community of volunteer developers, operators, and outreachers teaching people how to use Tor and stay safe online. And there are dozens of researchers at NRL and elsewhere who've written thousands of papers on onion routing. Thank you for this recognition of our work.
We're extremely grateful and honored for receiving this award.
Our sincere gratitude to the selection committee and the community.
Indeed. And it is a particularly special honor to receive the Test of Time Award for this work, which is centered around harnessing the passage of time to create the asymmetry needed for publicly verifiable message authentication codes.
The project essentially started in 1997, when I started my PhD at CMU. My advisor, Doug Tygar, gave me the following problem to work on. Consider the distribution of advertisements on the internet. Such advertisements could be broadcast to receivers. Network providers could switch the advertisement and profit themselves. So how can receivers efficiently authenticate broadcast information to make sure it originates from the correct sender?
It is incredible the foresight Doug had to pose this problem, as internet advertising was still in its infancy at the time.
Not just advertising. The internet itself was in its infancy in 1997. Certainly, PKI and the ability to digitally sign and verify efficiently was much more primitive than it is today.
Indeed, I was initially quite perplexed by the problem and didn't make much progress on it, as all the approaches seemed insufficiently efficient. I kept thinking about the problem, and 2 years later, during an internship at IBM Research, The basic idea appeared while in the evening reading a relatively unrelated paper on multicast key distribution.
We then worked out the basic Tesla system, adding the one-way keychain to achieve robustness to packet loss.
I remember the day that Eugene walked into my office in summer 1999, all excited, and started drawing boxes on the board. I was working myself on a broadcast authentication scheme at the time, and the solution looked to me like a cheat at first. It looked too simple, and the reliance on the synchronization for authentication seemed like a non-starter. But then I got convinced that the synchronization requirements is actually reasonable, and the solution might actually work.
After arriving at Berkeley, Doug suggested the use of amortized digital signatures, which then led to the chain signature verification scheme as the second part of the paper.
Doug didn't like the initial name for the system, which we called Magma. Incidentally, Benny E. was visiting and suggested the name Tesla.
As a big fan of Nikola Tesla, I immediately liked the name.
I wasn't sure at first. What does an authentication scheme have to do with a futuristic music instrument? Little did we know that this instrument is going to be the least of our problems with name collisions with futuristic things.
Initially, people didn't like the need for time synchronization of Tesla, but without that, alternative systems had a much higher overhead.
Over the past 20 years, the Tesla authentication system was used in a variety of real-world applications. Today, Tesla is being considered for the authentication of satellite navigation messages.
In fact, already in the early 2000s, it was considered for standardization as a multicast authentication scheme at the IETF. It became an RFC in 2005, and we should mention that Bob Briscoe is a co-author of that RFC.
First, let me talk a little bit about the paper on searching unencrypted data. The problem is how to design an encryption scheme that, while protecting the confidentiality of the data, allows a server to perform search on the encrypted data. The problem was initially inspired by a presentation by Kubi, a faculty in EECS at Berkeley, on Ocean Store, a global federated network of storage nodes. One of the research challenges was how to simultaneously achieve data confidentiality and utility. Since data would be stored on untrusted storage nodes, it had to be encrypted. But how can we achieve utility and enable searching the data if it was encrypted? I found the question intriguing and kept thinking about it after the presentation. The same day, I came up with an initial approach, and with David Wagner and Adrian Perrick, we worked together to develop a much more efficient solution. The final algorithm in the paper was simple and elegant. There was no crypto class offered at Berkeley at the time. I remember learning crypto by reading online lecture notes and papers. In particular, reading through Michael Blair's notes was very helpful even when I was writing the paper. The paper was published 21 years ago, and it was my first paper and presentation at the IEEE Security and Privacy Symposium. The problem setting predates the rise of cloud computing by more than a decade. We were one of the earliest to work in this domain. Searching over encrypted data, and more generally, computing over encrypted data and secure cloud computing has since grown into active research areas with volume of work and real-world applications and deployment. Doing work early in a new domain does present unique opportunities for groundbreaking exploration.
We're extremely grateful and honored to receive this award. We'd like to extend our sincere gratitude to the selection committee and the community.
Our paper's setting is in sensor networks, an early version of distributed IoT nodes. As sensor network nodes have severe resource constraints, they cannot efficiently perform asymmetric cryptographic operations.
The project started with the breakthrough idea by Echenor and Gligor that was presented in their seminal CCS 2002 paper, a key management scheme for distributed sensor networks. Their idea was to select a pool of symmetric cryptographic keys to provide a subset of keys to individual sensor nodes.
Two neighboring nodes would then determine which keys of the key pool they had in common, and if they had at least one common key, they would use that to protect their communication.
This elegant approach was intensely intriguing. As soon as Joan started his PhD at CMU, we immediately started working on these systems.
We extended the model of key distribution and established an approach for analyzing the security of such schemes.
By identifying 3 different ways of extending the resilience of the original key pooling scheme, we showed that key pooling was not limited to just a single algorithm, but was in fact an exciting problem space admitting a large number of approaches with different properties and trade-offs.
We could not foresee the tremendous community interest this research would incite, as many researchers started to embark and propose a series of ever-improved systems.
This wave of research has also helped to popularize the threat model of multiple node compromise in sensor networks and IoT. This threat model continues to be a fruitful source of research challenges today. We are grateful to have been part of this journey.
My name is Brian Parno, and on behalf of my co-authors, Adrian Perig and Virgil Gligor, I would like to thank the Test of Time Committee for this award. We are honored and grateful to receive it. We were proud of our work at the time, but we never expected it to have so much impact. This work started when Virgil, then a professor at the University of Maryland, visited CMU to give a talk. In the talk, he mentioned the challenges of detecting node replication attacks, and he observed that the node replication attacker is both stronger and weaker than the traditional Dolev-Yao adversary. Afterwards, Adrian and Virgil discussed the general notion of trying to detect replication via emergent algorithms, which produce a network-level property via the independent actions of many nodes. Shortly thereafter, I started as a graduate student at CMU, and Adrian pitched me on the project. While we exchanged many emails while writing the paper, it turns out that I would only meet Virgil in person the following spring at the 2011 Oakland conference where this paper appeared. Over the next few months, I fleshed out a protocol in which nodes sign their own location information and sent it randomly to selected witness nodes in the network. The security analysis used the birthday paradox to guarantee a high probability of detection. Unfortunately, this protocol was more expensive than we wanted, so I came up with a second protocol, inspired by a recent paper on rumor routing. The security analysis of our new protocol relied on Sylvester's 4-point problem and led me to make one of my few in-person visits to CMU's math library. 3 days before the deadline, we realized that our Python-based simulator wouldn't finish all of the tests in time, so over the course of several sleepless nights, I rewrote it in C++ to eke out some additional speed. As you may know, this adversary model and problem formulation captured the community's interest and led to some remarkable follow-on work. For myself, I am grateful that Adrian and Virgil gave me such a strong start to my graduate career, and that they have been such generous mentors ever since. From all of us, I would like to thank you again for this honor.
Congratulations to all the authors of the award-winning papers. These works are astounding achievements and something everyone in our community should be proud of. Many of the award winners are here today, so I hope you'll join me in congratulating them in the conference Slack, as well as in person, at least virtually, in our Zoom room after the ceremony. Thank you.